Okay, section 9.3, the chain rule. The chain rule, dy dx, is used to differentiate functions that are composite functions. So if your function y can be expressed in terms of u, and then u can be expressed in terms of x, then we can apply the chain rule and it will be dy du. So simply that function differentiated followed by du dx. So this function differentiated. Here is just a different way of writing this result. So dy dx is your f differentiated followed by g differentiated. Okay. You need to express the final answer in terms of x. So return to x variable if you use the replacement. So that works for composite functions. So over here you could see that you have got a couple of functions going on. There's more than that, but you could think of the two main functions going on. You could see that inside the bracket you have got this 3x to the power 4 plus x. This is the inside function. And then this bracket is raised to the power of 5. So what we can do, in order to find dy dx, we need to find our outside function. So this is going to be y equals to something to the power 5. So we're going to replace that inside function with u. There you go. Okay, and what is our inside function? So what was our u? It was 3x to the power 4 plus x. There you go. So this expression can be thought of something which is our u to the power 5, where my u is equal to 3x to the power 4 plus 5. So this is our inside function u. And now all we need to do is differentiate both. So we're going to find dy du. That just goes to 5u to the power 4. And here we've got to do du dx. So that will go to 12x cubed plus 1. And to obtain the final result, we are going to use our chain rule. So dy dx is dy du times du dx. It's really easy to remember. Although they are not fractions, they do behave like fractions. If you were to cancel it down, you end up with dy dx. So literally just multiply these two together. So you've got dy dx. Because I've quoted the result over here, I don't need to write it again. I just can write the multiplication. I said I want to do 12x cubed plus 1. Okay, but what have we got here? We've got u's, and we need to return back to our x's. So our u is 3x to the power 4 plus x, and then 12x cubed plus 1. So I've used the 5 times our bracket to the power 4. So 5 comes down, reduce the power by 1, and then you've got the bracket to the power of 4, followed by the bracket differentiated. Okay, so let's have a go at example 7. So here we've got sine to the power 4x, and we have to find dy dx. We'll look at some general rules in a minute, but over here what we've got is y equals to, you need to realize that we've got sine x to the power of 4. So we are going to replace our inside function, which is our bracket here, with u. So it's u to the power of 4. So, but what was u? U is sine x. we're going to differentiate both those functions. So we're going to get dy du. That will go to 4u cubed. And we're going to find du dx, and that is going to be cos x. And then we're going to use our chain rule. So our chain rule is, always quoted, dy dx is equal to dy du multiplied by du dx. So dy du is 4u cubed, and du dx is cos x. I need to make sure I return to x's. So u is equal to sine x. So I've got 4 sine cubed x multiplied by cos x. And that is my answer. So what about those general results? So this is the function to the power of n. So this is your power function. So you've got something to the power of n. When you differentiate, the power comes down, and then you reduce the power by 1. But obviously you must not change that bracket. Whatever is inside the bracket needs to remain the same. And then you need to follow it by the derivative of that inside function. And these two need to be multiplied together. So you can apply the chain rule over here in a very quick way. So the power comes down, reduce the power by 1, and then differentiate the inside function, and you do the multiplying. Here's another way of writing the same result. If you've got composite function, f of g of x, clearly g of x is fed to f, so that's the inside function. You differentiate the outside function, f, but it's in terms of g of x, and then you multiply it by g differentiated. So let's have a go at example 8. Got a function, square root of 5x squared plus 1. So let's rewrite it first. So you've got 5x squared plus 1 to the power of a half. And this is really obvious. You could see that the inside function is 5x squared plus 1. So the intention is to use this result really quickly. So if I differentiate it, I need to use that red thing to the power of a half, so the inside function to the power of a half. The power comes down, the inside function stays there, you reduce the power by 1. There it goes. And then you multiply it by the inside function differentiated, so it's 10x. Tidy it up. Now, normally I would say if you are using this result to find something else in the question, like in this question, don't bother with tidying it up. You can actually find dy dx straight away by substituting here x is equal to 4. But I will tidy it up just so we can check whether, you know, what to do in this case. So let's just do the question first. So it's 5 times 4 squared plus 1 to the power of minus a half multiplied by 10 times 4. Pop it into the calculator. 5 times 1681. Square root of 81 is 9. Flipped is 1/9. And 2 and 2. So is that 20 over 9? Let me just double check that this is right. If it's not, then we'll have to pop it into the calculator. That's correct. Okay, so over here, if you want to show it in a tidier manner, the 2 over here and 10 cancel. And then you've got 5x in the top of the fraction, and you send this into the denominator. So that's an alternative way of writing this answer, if you had to write it in this form. Okay, so we're just moving on to one more example, and a new important rule that needs to be introduced, which I actually introduced to you before in the previous section. Okay, so dx dy is equal to reciprocal of dy dx, and dy dx is reciprocal of dx dy, so it's literally flipped. So because you might have lots of functions that you have you are not able to write y in terms of x, but you have x in terms of y. Therefore, like in the example 9 over here, we've got y cubed plus y is equal to x. So dx dy can be found. So we are going to differentiate x with respect to y. So the x's and y's swapped roles. So it's going to be 3y squared plus 1. To find dy dx, we are just going to flip our dx dy. So it's going to be 1 over 3y squared plus 1. So here you've got the derivative in terms of y. So if you want to find the value of that, we're just going to sub y coordinate. It only relies on the value of the y coordinate. So it's 1 over 3 times 1 squared plus 1, which gives you 1/4. There you go. You can have a go at exercise 9C.